Okay, basics of hashes. Let's suppose that we have some input, some number, and for the purpose of this exercise, all our inputs will be numbers. Let's suppose we have some sort of number that we want to hash. So we want to produce a hash of that number. Now, let's say that we have a simple hashing function which checks if a number is even or odd. And based on that calculation, it will output either E for even or O for odd. So the number of possibilities here, if we have a n as an input number, the number of possibilities here is either E or O for odd. We have two possible hashes for any given number that we feed into this hashing function. This hashing function is very, very simple and not at all secure because it is very easy to get the same hash for different inputs. Imagine, for example, if you were using a hashing function to securely hash your password in a database and then somebody got their hands on those hashes. Now, if those hashes were just E's and O's, it would be fairly easy for the perpetrator to get into the system. All he would have to do is try certain numbers until the hash matches the hashed password that you've already provided. What this means is that if you use the number 15 as your password, you would get a hash O because 15 is an odd number. But if the attacker tried to log in with the password 33, he would also get the hash O, so the hashes would match. And then the attacker would enter your account with a completely different password purely because the hashes match. This is why simple hashes are not enough as a password security. Now, let's take it up a notch. Let's make the hash a little bit more complicated. The first stage will still remain. So we have the letter N, or our input number, and then it can be either even or odd. So it's going to be E for even or O for odd. Good enough, right? But now let's suppose that since numbers have digits, if we sum up all the digits in our number, if that sum is divisible by the number 3, then let's, for example, add the letter G. If it is not, let's add the letter Q. So if we have the sum of digits in n, let's see if that's divisible by 3 or not divisible by 3. If it is divisible by 3, let's add the letter G. If it is not, then let's add Q. How many solutions does our hash have now? How many combinations are possible? Well, right now, there are 4 combinations possible. So, we have EG, EQ, OG, and OQ, depending on the number that we feed into the hash function. So we have 4 possible hashes resulting from this. EG, EQ, OG, and OQ. Cool, right? Pretty simple. Now, if we used this approach to hash a password in a database and secure it, the perpetrator who's trying to hack our account would have to work slightly harder to find a collision. Now, when a different input results in the same hash as another different input, this is called a hash collision. When a hash collision is discovered, that hash is no longer considered secure and should not be used. This has happened in some hashing algorithms before, and as computers get more powerful, they discover these collisions much faster, and this is why we have to upgrade our hashing algorithms periodically. So in our case, we now have 4 possible hashes resulting from our input. Now, you can add a bunch of other conditions that will extend this hash and make it more complicated by adding more mathy operations on top of the ones that you already have. And the most complex hashing algorithms have thousands upon thousands of complex math operations applied to these numbers that basically make the ending hash irreversible. It is not possible in a reasonable amount of time to calculate by going backwards which number was the input. For example, if we add to our existing algorithm here the condition that if the sum is also divisible by the number 7, so if we can divide by the number 7, then let's also make it so if it's divisible by the number 7, then let's just do nothing. But if it's not divisible by the number 7, let's make the letters and numbers lowercase. Let's make the letters lowercase. So then we will have the twice as many hashing options available, which will become lowercase e, g, and lowercase eq and lowercase og and lowercase oq. So we now have 8 possible hashes here. We can extend this further by adding, for example, something like checking if the rounded half of this sum is a prime number. So this is a slightly more complex check, and then we can add to this hash another letter based on that. But enough about this theory, let's see this in code. Okay, let's see how our algorithms perform as code. These are some example files that I whipped up in JavaScript. If you don't know JavaScript, doesn't matter, this is all fully discardable. You don't have to bother with this. What this test-hash.js main file does is it simply imports the individual hash functions that we've developed as separate files and then uses it on the input we provide through an I flag. You'll see how that's used later. Actually, let's demo it right now. So this is node and test-hash.js -i, and then you provide a number like 20. So we have here the main file is importing hash1. Let's see what's in hash1. Hash1 contains our basic even or odd checker. If the number is even, it will return even, otherwise it will return odd. Let's try that out. 20, we get E. 21, we get O. So even and odd, this works. You can go as large as you want within certain limits that are imposed by JavaScript itself as the environment. So we have O for a big number, or if we change this to even, we get E for the even number. Simple, our hash works and has 2 possible options, O and E. Now let's check out hash 2, the slightly more complex hashing algorithm that we built. So if we switch this to hash 2 and check out what's in here, we'll notice that first, as the input is received, we get the sum of all digits in the input. Then we get 2 variables, result1 and result2. Now result1 is going to be the same one as in hash 1. It will either be E or O depending on whether the number is even or odd. The second result will be either G or Q based on the divisiveness of the sum by the number 3. So if the sum of digits is divisible by 3, this means that the modulo is 0, which means this phrase means that it is divisible by 3. Then we apply G. Otherwise, we add Q. Combined, these two are R1 plus R2, so either EG-EQ or OG-OQ. Then we have another condition. If the sum, when divided by 7, has any leftovers, it will return as is, so uppercase. Otherwise, which means that it is indeed divisible by 7, it will be turned into lowercase. So now if we test this on the same numbers that we used before, we get EQ lowercase, and for just one digit being different, we get OG uppercase, completely different in every regard. So we have 2 completely different hashes for very similar numbers. Now let's try a slightly smaller number, which we can also manually check. 123, we got OG. All right, we have a hash collision. So number 223827881 and 123 have the same hash resulting from our hashing algorithm number 2. It is a proof that our hashing algorithm is not secure. But let's check 1, 2, 3 if the hashing was done correctly. So we have a sum of all the digits, which is 6, 1 plus 2 plus 3. Then we have a R1, which will either be E or O. This should be O, and it is indeed O because the number is odd. We have result 2, which checks if the sum is divisible by 3. If it is, and it is because 6 is divisible by 3, we get G. That's good. It is uppercase. Why is it uppercase? Well, because if we divide the sum, which is number 6, by 7, our remainder is still 6. 6 equates to true in JavaScript. So when you check any value, if it's true or false, it will only be false if it's 0. So anything other than 0 is true. In our case, that's 6, which means true. So the first condition is returned, which is the regular combined. That means the uppercase one. If the remainder were 0, which means that the sum is indeed divisible, then it would be lowercase. And we can actually check this by turning the number 3 into 4. And now we have the sum is 7. 7 is indeed divisible by 7. And we have lowercase EQ. So our hashing algorithm number 2 works, but it is very insecure, as we've proven, because it is easy to reproduce the same hash for different inputs. Now let's take a look at hash 3, a slightly more complicated version of hash 2. First, let's change our main file to use that one, and then let's take a look at what it does. So the first few lines, the first 8 lines, are the same as in hash 2. It is exactly the same. What's different here is that we first grab half of the value of the sum of digits. So if the sum of digits, for example, previously we had the sum be 6 and 7 respectively, then we take the half of that. We divide the sum by 2. If it's 6, that's going to be 3. If it's 7, it's going to be 3.5. We then round this number, and that's going to round up, which means that in the case when the sum is 7, the half is going to be 4, not 3, 4. Then we have a check. If that resulting number is a prime number, then we add t to the end of our hash. Otherwise, we add w, both lowercase. Is prime is just a simple function that we've defined below here. Nothing complicated, it just checks if a number is a prime number. So it's just a custom function. So now we have an extended version of our hashing algorithm, which we can test here. So we have for 1, 2, 4, we get the EQW. For 1, 2, 3, we get OGT. Now we have a 3-letter hash that has uppercase and lowercase letters mixed from time to time, so that's a lot more combinations to play with. Still, it is very easy to produce a conflict. It is very easy to find a hash collision, and this hash is not safe either. I want to show you one last hashing algorithm, and that's the secure hashing algorithm 1, which ironically isn't really secure anymore. It is now recommended not to use it because a lot of hash collisions have been found with it, and it is used here as a demonstration only. We are going to be using a ready-made version from the npm package manager for JavaScript, which means that I didn't re-implement it from scratch here, so that's why the code is this simple. We'll use it in the hash4.js file like so. Hash4, again we provide the input, and if we put in 1, 2, 3, you will now notice that we actually get a big hash with a lot of letters and numbers, so there's a whole bunch of them. And if we just change one digit, the entire hash is completely different. So this used to be a secure hash because it's very long, it's very difficult, it is impossible to reverse engineer because of the math that's being applied to the input here, but it is also very difficult to find collisions because you would have to try very many inputs before you reach an input that has the same hash as another one that you've tried before. Very strong computers are having a very hard time doing this, and this can only be done with extremely powerful machines. However, despite this being possible only with powerful hardware, whenever a hash collision is found, that hash algorithm is considered insecure because there's always somebody out there with a more powerful machine. So you should not use this in real life. There are other more secure algorithms to be used today, like SHA-256 or even more advanced ones. But in general, SHA-1 is now insecure, but it's a nice demo of what you can get from a hashing function. So long hashes that are provably unique across many different inputs. Another caveat I'd like to mention is that with hashes, they are always the same length, right? Our third version of the hash always had 3 characters in the output, and no more, no less. The same goes for the demonstrated secure hashing algorithm 1, SHA-1, which always produced a fixed number of letters and numbers in that resulting string. Now, if you encounter a website which asks you to register your account, and when you're putting in your password, it says the password cannot be longer than a certain number of characters, that means that they are not hashing your password. What that means is that if an attacker gets their hands on their database, they will find your password saved there as you've typed it in. They will not obscure it, they will not mask it in any way. We know this because if they were doing this, then they could just set the entire database field for storing passwords to the length of the hash, and the length of your password wouldn't matter because regardless of the input that you put in into a hashing function, the output has always the same length, which means you can always save it in the database. So if my password has 10,000 characters or 3 characters, I'm always going to get, for example, a 32 length hash out of it, which is immediately storable in the database. So keep that in mind. If a website asks you to limit your password character length, treat it as very suspicious, and for best results, ask them about it. Ask them to prove to you that they are hashing your password and keeping it securely. Otherwise, do not register your account there unless you don't care about it being breached. I hope this crash course into hashes and how they work and how they're composed was useful to you. If you have any feedback, please let me know in the comments below. And if you like this video, subscribe and stay tuned for more explainers like this one.